Lagrange multipliers find constrained optima, but geometrically, why does setting gradient vectors parallel actually work? Take a slanted plane objective function f of x and y equals x plus y, constrained to a flat circular boundary x squared plus y squared equals 1. When you walk along this curved track on the circle in the direction of its tangent vector, r circle equals the vector negative y comma x, your step diagonally moves you in the x and y directions simultaneously. Delta r equals the vector delta x comma delta y. As long as that diagonal step is not perpendicular to the objective function's slope, given by the gradient of f equals the vector 1 comma 1, your net height f actively changes due to the non-zero dot product. Delta f is approximately the gradient of f dot delta r, which is not equal to 0, which is dependent on varying r circle values. But at the exact peak, f max equals the square root of 2, where the point x comma y equals 1 over the square root of 2 comma 1 over the square root of 2, your x component step reduces net height as much as your y component increases the net height. R circle equals the vector negative 1 over the square root of 2 comma 1 over the square root of 2, creating a dot product and net height change delta f of 0. A zero change in height delta f means the objective function slope, the gradient of f, is perpendicular to the tangent vector, delta r, along the circle constraint curve. The circle's gradient vector, the gradient of r, is always perpendicular to delta r. If both gradients, the gradient of f and the gradient of r, are perpendicular to the delta r, they must point along the same parallel line. So by setting these two gradient equations parallel, the gradient of f equals lambda times the gradient of r, you pinpoint the coordinates x comma y where lies the true peak along the constraint curve, r.